Okay, we are talking chapter 16 here. So we got into sort of thermodynamics. And remember, sort of the study of thermodynamics and sort of what we're looking at a lot of times is whether or not a reaction, again, is sort of spontaneous. And when we talk about a reaction, again, being spontaneous, as we talked about last time, it really doesn't have to do with anything in terms of how fast or slow the reaction will take place. Although, again, sometimes people sort of hear the word spontaneous and think like it happens really immediately. What we're talking about here really is, again, whether or not under sort of those conditions, will this reaction basically take place without any sort of intervention of outside influences. And if it is spontaneous, that usually will mean that the way the reaction is written, it should start to head towards the product side. Obviously, if we have sort of a non-spontaneous process, the opposite is true. Under those conditions, it really wouldn't be expected to occur, and kind of going to hang out, over here on the reactant side. The way it's written is not going to really go towards the products. Again, a reminder that you can have a spontaneous reaction that's super slow. You can have one that's like really, really fast. So again, it has really nothing to do with sort of the speed of the reaction. Again, that was kinetics that we talked about that kind of dealt with that aspect of it. We talked about a couple of things that help us maybe decide whether or not a reaction is to be spontaneous. One of the new sort of values probably is delta S, which is the change in entropy. Again, not to be confused with our classic delta H, which is the change in enthalpy. And delta S is about disorder. And obviously, delta H is all about heat and energy, basically. So remember, for the delta S, as the amount of disorder increases, the delta S actually will become more positive. So with an increase in the disorder of the system or even the surroundings, we will see an increase in the entropy. And again, that is reflected typically in a positive sort of value for our delta S. Again, that's a little bit different in some senses. A lot of times we think of negative as things sort of happening and being bigger, but here positive here for our delta S. And obviously, as we decrease the disorder, which by the same token would be increasing the order, we will see a more negative delta S. Remember that when we use delta S, we do look at delta S of the universe, and that is the delta S of the system or the reaction, plus the delta S of the surroundings. And we needed basically both of these components to sort of determine whether or not a reaction is going to be spontaneous. If you do that and it ends up being a positive value, then the delta S of the universe is positive, then the reaction would be spontaneous. Obviously, the opposite is true. If it's negative, it would be non-spontaneous. To calculate the system versus the surroundings, there are some different ways to do that. So obviously the delta S of the system is kind of like any other sort of thermodynamic sort of property. We can look it up in a table, take the delta S of our products minus the delta S of our reactants. And like normal, when you look it up in that sort of thermodynamic table, you want to make sure, thank you, you want to make sure that you find the right substance in the right state. Also different in the delta S table, as we talked about, you will find values for things like H2O2, things in their standard state, which you typically don't find values for delta H or even delta G. You could also make, as we saw last time, a fairly good prediction based off of the equation as to whether or not you expect the delta S of the system to be positive or negative. Again, if you created more gas molecules, for example, than you started with, you're going to have a lot more disorder on your product side, and you would see a positive delta S. Opposite is true if you kind of ended with less gas molecules than you started with, then you would have a little bit more order happening, not as much things flying around, and you would expect the delta S for that reaction to be negative. Remember, again, alone, it doesn't tell you if the reaction is spontaneous or not. It just tells you in that situation, is the order or disorder increasing or decreasing. Delta S of the surroundings is related to our delta H, so it's net minus delta H of the reaction divided by the temperature in Kelvin. And remember, it's sort of an opposite relationship here, and that's why we do have the negative in this formula. If you have an exothermic reaction, which is going to give off energy to the surroundings, that means that the surroundings will pick up that energy. And in normal temperature situations, you would expect an increase in the entropy of the surroundings, and thus that negative for the exothermic reaction for delta H plus the second negative there will turn your S into a positive, which is what you would expect. And vice versa, if it's sort of an endothermic reaction, it's going to pull the energy from the surroundings, and we would expect everybody kind of slow down and have a little bit more order, and that would be a positive delta H, and a negative here will give us a negative for our delta S of the surroundings. So again, that is why we have the negative there. We then talked about delta G, which is Gibbs free energy. And that is energy available to do some type of work. And there's a few different formulas we'll see with delta G, but one that we saw, delta G equals delta H minus T delta S. So again, if you have the delta S and the delta H, you can calculate the delta G of the reaction. A reminder, right, of units here. That is typically in kilojoules, and again, our S is typically in joules. So you do want to watch units again if you're using that equation so that everything cancels out correctly. And you can also just calculate delta G by the classic products minus reactants, right? So you could go again to your table and do your products minus reactants. We actually can use delta G directly to figure out whether or not a reaction is spontaneous or not. So if we end up with a delta G that's negative, then the reaction is going to be spontaneous, should head towards the products. If the delta G is positive, it's going to be non-spontaneous. And if the delta G is equal to 0, then you're probably at equilibrium at that point. Any questions on any of that stuff there? All right, so we finished up on an example, I think, last time, so we'll continue on. Taking a look at this formula here for our delta G, which is equal to delta H minus T delta S, we can make some predictions just knowing, for example, the sign of certain things as to whether or not we would expect the reaction to be spontaneous, or what conditions would be necessary for the reaction to be spontaneous. So if we just kind of, I'll just write this a few more times here. We can look at each sort of situation. This way, I think. All right, so let's take a look at some of these situations here. We'll go here first into this box. So if we have a delta H, which is endothermic, that means that this guy here will be positive. And we have a delta S that is also positive. What we will see is the delta G here will only be spontaneous at high temperatures. Or you will need really high temperatures for it to be spontaneous. And that is because, again, a reminder that the delta H is kilojoules, this guy is joules, so it's got a big jump on it. And the only way for it to become negative delta G is this back part of the formula here has to be larger than the front part. And the only way that's going to happen is a really large value here for temperature will allow that kind of back part of the formula to overtake the front part that's positive, and you end up with a negative delta G. At low temperatures, the process is not going to be spontaneous. So if you have positive H and positive S, you would need a high temperature for that reaction to become spontaneous. And if you have a lower temperature, you probably could predict that that reaction would be non-spontaneous in that situation. Any questions on that one there? Let's go to the next box here. We'll go with that one too. We'll just come up here. And we're going to have a delta H that is exothermic. So now we have a page that left. There we go. Now we have a delta H here that's negative. We also have our entropy that is positive. So this is a good deal because this is positive. This is temperature in Kelvin, which has to be a positive number. That means the back end here is negative and the front end is negative. So you're basically just adding two negative numbers together. No matter what you do at all temperatures, you will get a delta G that's going to be negative, and this reaction should be spontaneous at all temperatures. So if you got negative delta H, positive S, that's a great situation. You could expect pretty much any temperature is going to be helpful there, and it's going to result in a negative delta G, and the reaction is going to be spontaneous. Now, if we look at the other two sort of situations here, we'll go 3 right there. And in 3, we are back to an endothermic delta H, so that's going to be positive. And now we have a decrease in entropy, so that's going to be negative. And that's going to be kind of important because with that negative delta S, that's going to turn this back part into a positive number. Front part's a positive number. That's bad because now we're going to get a delta G that's going to be positive at any temperature. And that means that it's going to be non-spontaneous, right? So in this situation, that's kind of the worst situation in terms of spontaneity, is a endothermic process. So you're not really gaining a lot of spreading out heat and stuff. And we're kind of getting everybody into a nice ordered type of situation. It's going to result probably in a non-spontaneous process at any temperature. Lastly, here, if we look at sort of the fourth situation, we have our delta H, which is exothermic. So again, we have a delta H here that is negative, and our delta S is also going to be negative. So once again, because our delta S is going to be negative, it's going to turn this back part into a positive number. And this means that at low temperatures, this reaction should be spontaneous, and that will give you a delta G that is negative. And that is because at low temperatures, it will keep the positive number smaller than the negative number. So when you add them together, you'll still get a negative number, and that would make it spontaneous. Now, obviously, at high temperatures, you're going to probably run into some troubles because at high temperatures, you have the potential to make this back part larger than the front part, and you could end up with a positive delta G in that case. So these are, again, sort of questions that's very commonly asked sort of in thermodynamics sort of chapters. Again, they sometimes don't even give you sort of numbers or values or anything like that, but they give you something like this, like, hey, this is positive, this is negative, you're at like a low temperature or something like that. Would you expect this reaction to be spontaneous? Obviously, you could just throw some numbers in if you want to, but again, these are sort of our situations that could occur. Any questions on that there? So let's talk a little bit about spontaneity. So let's say we're doing this reaction here, low calcium carbonate decomposing into calcium oxide and a little CO2. The delta H is 177.8 kilojoules. The delta S is 160.5 joules. So why don't you calculate delta G at 25 degrees and see if it's spontaneous. So take a moment there and calculate it up. Let's take a look at this one here. So we have H and S, as we talked about before. We're going to see a few more equations with delta G in it. So obviously, I would choose the one that sort of has those values. So we go with delta G is equal to delta H minus T delta S. So obviously, we need to convert some temperature here into Kelvin. So we'll add our 273 to it to get 298. We're going to put our values in here. So our delta G is going to equal, once again here, as I mentioned, I think last time, I'm going to convert my kilojoules into joules. So everybody's in the same units. You do got to watch, again, the units on both of these. You could go kilojoules on both. It's your call. Minus T, which is my 298, and my S, which is 160.5 joules. If I do all that good stuff there, that's going to get me 129,971 joules, or approximately 130 kilojoules here. as our delta G for this reaction. First off, any questions on the calculation? Again, a reminder, don't leave 1 in kilojoules, 1 in joules, otherwise you're going to be off. This is a positive value for delta G, which means this reaction is non-spontaneous at 25 degrees Celsius, right? And this we would kind of predict a little bit because as we just talked about here, we have a positive H and a positive S. And we know that in that situation, as we just talked about, a low temperature is not going to help us get that back part of the equation larger than the front part of the equation, since it's obviously, I got a 1,000-fold jump on it anyways, with it being kilojoules up front. So can we, though, figure out at what temperature this reaction may become spontaneous? And we can. So, for example, we could use this same formula here, and we could use it to help us predict perhaps what temperature this reaction may become spontaneous. So the temp becomes spontaneous. We know that definitely delta G's got to be negative, so that's on the other side of 0, right? So I'll just set that equal to 0. Delta H minus T delta S. Here I'm going to bring my T delta S to the other side, equals delta H, dividing by my S there, gives me T is equal to delta H over delta S in this case. So if I take those guys, we'll take my H, which again is 177.8. Again, I'm going to times it by 1,000 so that they are both in joules, and divide it by my bottom one that is in joules. And that's going to get me here 177.8 times 1,000 divided by 160.5. That's going to get me approximately 1,108 Kelvin. That's the Kelvin comes from there. And this is the minimum temperature at technically where this reaction would become spontaneous. If I subtract a little 273 action from that, that's going to get me 835 degrees Celsius. Heck, I see that right there on my map there, or my graph. And that is the temperature at which this reaction would become spontaneous. I would definitely classify that as a high temperature, which is, again, in this reaction would be necessary, obviously, to get that back part higher than the front part in terms of turning it into a negative. Now, what were we looking at in this graph before I scribbled all over it here? That is the partial pressure of CO2. And since CO2 is the only gas present, you can see no CO2 is being made, which means this reaction is not occurring. And we do start to see some of it actually before 835, but at 835, we hit the magical pressure of standard pressure of 1 atmosphere. So we hit that standard 1 atmosphere at about 835, which will be that sort of condition. So this equation is sort of twofold in a sense. You can use it obviously to predict whether or not obviously the reaction will be spontaneous. And in a situation like this, you could potentially use it to figure out at what temperature that reaction would need to be for it to turn spontaneous if possible. Any questions on that there? Again, the key with this formula is definitely watch those units, kilojoules and joules. All right, so let's try this one here. The following reaction, minus 1204 kilojoules for the delta H, minus 216 for the delta S. At 25 degrees, our reactions or products favored at equilibrium under standard conditions. Okay, so again here we have an H and an S, so we'll go with our delta G is our delta H minus T delta S. So popping in our numbers here, we got a negative 1204. Again, I'm going to multiply by 1,000, convert to joules, minus, we do need to convert that obviously to Kelvin, to 298. So 298 Kelvin here, and our minus 2.16 to 16.4 joules Kelvin mole. All right, so popping that in there, we're gonna get negative 1204 times 1,000 minus 298 times negative 216.4 can get us negative 1139513 joules, or we could clean it up a little bit, bring it back to kilojoules, maybe negative 1140 kilojoules in this case. And obviously here we do have a negative delta G, so that should be a little bit of spontaneous, which means this reaction should be heading in this direction. So definitely products here should be favored in this case. Yeah. Any questions on that there? So sometimes people will sort of talk about more are reactants or products favored as opposed to spontaneous or non-spontaneous as well. So it's kind of the same sort of question in a lot of cases when you see that. Any questions on delta G here? All right, the next thing we're going to talk about is phase changes and involving energy. So if we take a look at phase changes, as we talked a little bit about, I think last time as well, remember that as we go from say solid to liquid or liquid again back to solid, there is that delta H of fusion, which is the energy required really just to do that change. Remember that does occur at the same temperature. And also we have a similar one as we go from liquid to gas and gas back to liquid. That's the delta H of vaporization. Also occurs at the same temperature. That's when we just change the substance, but we don't change the temperature of anything. This happens at the normal boiling point, right? And perhaps melting point, freezing point over here for our delta H of fusion. So when we have a phase change, we are actually at equilibrium because both phases are happening at the same time. Again, it's not until you get a little bit above, for example, 0 degrees when we're talking about water, that you fully transition to liquid water, not until you live below 0 degrees that you really sort of fully transition to ice at exactly 0 degrees. Again, you got kind of like ice crystals happening. Both phases are happening at the same time. So because this is an equilibrium situation when we change phases, delta G would equal 0. And if we rearrange sort of this equation, bring T delta S to the other side, we could actually solve for, in this case, the delta S. And the delta S, as you can see over there, would be our delta H divided by T. And in this case, this could be our entropy of fusion, could be our entropy of vaporization, depending on what transition you're doing. I will bring a note to you here that if you take a look at this equation, it should look kind of familiar to you, as that again is the equation that we use for surroundings, right? Except the difference is there is no negative on this one, yeah? So this is not the one that we use really for the surroundings, even though it looks exactly like it. This is the one we kind of get for our phase change, so we don't have that sort of negative in there like we do for the surroundings. So this is the one sometimes people kind of put the negatives in the wrong spots when they go to use these guys. So if we're looking at this particular transition here, this is liquid water going to basically steam, right? So that's the transition happening right about here. And in this case, we are going in this direction, which means that we're going from liquid to gas, and that is an endothermic process. Hence why our delta H here of vaporization for water is positive, because this is an endothermic process going in this direction. By the way, the 373 here reflects the normal boiling point of water, which is 100 degrees Celsius. That if you add 273 to it, you get 373 Kelvin, right? So that is a normal boiling point of water and where this transition basically occurs. And you can see here we do get a positive value here for our entropy, and this would be known as the entropy of vaporization of 109 joules per Kelvin. That is a positive number, which again sort of makes sense based on the direction we're watching, which is our liquid water is going to gas, right? So we're going from a more ordered state to a more disordered state with gas molecules flying around. we should expect the entropy to be positive. Now, if we were going in the opposite direction, say we actually were going from gas back to liquid water, say in this direction, like condensation, right? And we want to say the entropy of condensation. The only difference in the calculation is this is no longer a endothermic process going in that direction. It's a exothermic process. So this would be negative 40.7 divided by 373 Kelvin, and that would get you a negative 109 joules per Kelvin, which also makes sense if you're heading in that direction, because in that direction you're going from gas molecules that are flying around to liquid molecules that have now kind of come together a little bit in a lot more order, and we would expect obviously our um, entropy change here to be negative as it's creating more order in this situation. So, a couple other things, obviously, we oftentimes use water as an example, right? For like heat of fusion, heat of vaporization. And we use like 100 degrees Celsius and 0 degrees Celsius as like the boiling point and melting points. But that is for water. So if you are using some other substance or dealing with some other substance, they will have different heats of fusions, heats of vaporization, and different boiling points and melting points. So just keep that in mind. Sometimes people auto roll with like 100 on every substance and like those numbers for every substance. So obviously it would probably be somewhere you could find those numbers, but it's not always going to be obviously the same values that you use for water because they're different substances. Any questions on that? This obviously works the same way for if we were doing some type of solid to liquid transition or liquid to solid. The only difference is we would use the heat of fusion for that. And again, as you go in the solid to liquid phase, that's an endothermic process heading in the opposite direction. It's an exothermic process. And same thing here, positive endothermic, negative for our delta H of vaporization heading in the opposite direction. So why don't you try one here? The enthalpy of vaporization of mercury is 58.5. The normal boiling point is 630. What is the entropy of vaporization of mercury? Okay, so let's take a look. So the enthalpy of vaporization, that is the delta H of vaporization, is 58.5 kilojoules per mole. So you can see we're dealing with mercury, definitely a different value than what we have for water. The normal boiling point here going to be 630 Kelvin, also a different boiling point than what we see with water. So again, we'll take a look at our equation here. And obviously we're at the enthalpy of vaporization, so we are doing the transition of liquid to gas, basically. And that means that our delta G here should be 0 because it should happen at the same temperature in an equilibrium situation. We once again can rearrange this equation by bringing this to the other side. That gives us our T delta S is equal to delta H. Dividing our T back over gets us delta S of vaporization in this case would be our delta H divided by our T. Once again, in this situation, we are assuming this process, as obviously they didn't mention anything about condensation, so we're definitely going from liquid to gas in this case, which should be an endothermic process. So this guy would be a positive number in this situation. So our delta S of vaporization would equal 58.5 times 1,000, just convert it to joules, divided by our temperature, which is already in Kelvin, which is nice. And that's going to get us here 58.5 times 1,000 divided by 630. It's going to get us something like 92.9 joules as our entropy of vaporization. Obviously, if you left it in kilojoules, just move your decimal place 3 places to the left there, and you'll have your kilojoule answer. This again is a positive value, which is what we would again expect to sort of be happening in this situation as we're going from liquid to gas, creating more disorder, and that should yield us a more positive value for our delta S. Clearly, if we were doing condensation, once again, the only thing that would be different is this would be negative, which would then turn this guy obviously into a negative value as you're going backwards. Any questions on that there? All right, we're gonna lay it up there, I think. Yeah.